Alright, in this chapter, we're going to focus on the principles, the laws governing the propagation of light rays. Okay? And these are called Snell's laws. Snell's laws. The Snell's laws actually have two parts. The Snell's law has two parts in it. Reflection and refraction. Okay, we have a medium here, in which light propagates with a certain speed, medium 1. And here is medium 2. It's a different medium in which the speed of light is different. Okay, now recall the speed of light in a vacuum is 3 times 10 to the 8 meters per second. What about the speed of light in different media, such as in glass, such as in air, such as in water? Well, the speed of light is not the same. Okay, in fact, they're all slower than the speed of light in vacuum. And as light reaches a border between two media, say this is air, this is water, okay? What's going to happen? Well, two things will happen. Light can reflect, so this is the incident light, I standing for incident light, R standing for reflected light, okay, so that's reflection. So the first part of Snell's law is what happens to the reflected beam. The second part of Snell's law is refraction, and that is assuming the second medium is transparent, such as glass, for example. Part of the light will actually get into the second medium. That's called refraction or transmission. Okay, so the Snell's law has two parts, for reflection and for refraction. Okay, let's first look at Snell's law for reflection. Okay, the Snell's law for reflection, it tells us, once we know the incoming or incident beam, it tells us how the reflected beam is going to go. That is the Snell's law of refraction. Okay, now, suppose we draw a line that is normal to the surface, to the boundary between medium 1 and medium 2, such as air and water. Okay, and there is an angle made between the incident beam and the normal. We call it theta I. Okay, theta I. That, or we call it theta 1. Okay, we can also call it theta 1. In fact, the textbook call it theta 1, so we're going to call it theta 1 as well. And this angle is the angle made between the normal and the reflected light. We call it theta 1 prime. Okay. Here, the index, the index 1 here means it's in medium 1. In medium 2, we call it theta 2. What does the Snell's law of reflection tell us? It tells us actually two things. One is the incident beam, the reflected beam, and the normal. These three lines are in the same plane. Okay, they're in the same plane. So if you make a plane out of these two lines, the reflected beam must be in the same plane. It's not going to go out or go down like that. That's one thing. Another thing is about these two angles. It says that these two angles are the same. It says theta 1 equals theta 1 prime. This is common knowledge. A lot of people know about it. Okay, and the question is, how do we understand this part of Snell's law? Can we derive this relationship, theta 1 equals theta 1 prime? Well, if you believe in Newton, you think of light as a bunch of particles, okay, that can collide elastically with this surface, then it makes perfect sense, okay? Think of a ping pong ball coming in and gets reflected off of that. It receives a force perpendicularly out like this. You see an impulse like that. Okay, there's no force along this direction. So the momentum in this direction is the same, and the momentum in that direction is just 100% reversed, and therefore these two angles must be the same. Okay, but we now understand that light is a wave. Right? Light is a wave. Even though we don't care about the wavelengths in this particular context, we still know that light is a wave. Is it possible for us to understand this relation, theta 1 equals theta 1 prime, using the wave nature of light? We have to understand it from the wave nature of light. Otherwise, you know, it wouldn't make any sense, because we do think of light as an electromagnetic wave. Okay, so is it possible to understand this from a wave point of view? Well, it turns out yes, we can. Okay, the derivation is a little bit more involved, but we can still understand why. You know, when light comes in, any wave that comes in like this, if the light ray comes in like this, it means the wave front must be like that, right? So at one point, the wave has arrived at this line here, the next moment is arrived at that line, that line, that line, that line, and the wave and the light ray which denotes the propagation direction, is perpendicular to the wavefront. Okay, it's perpendicular to the wavefront. Same thing for refracted light ray. The wavefronts would be like that. Okay, so here's what we're going to do. We're going to consider two beams. Okay, two light rays, parallel light rays within the incident light. Okay, within the incident light. So we have one beam, which is I, and we're going to draw yet another beam. Okay, I'm going to draw it right here for you. This is the border between 1 and 2. Normal line here. Okay, I'm going to draw one beam first. Incident light. Here's one beam. And I'm going to draw another beam parallel to it. Okay, so we can call it I and I prime, right? They're parallel to each other. They're parallel to each other. Now, these two light rays represent the direction of propagation. So we can think of what happens to the wavefront. The wavefront would be like this, right? Would be like this. They're going to advance like this. So at one point, right? At one point, the wavefront has reached here, perpendicular and perpendicular. So at that moment, for this light ray, this part of the wavefront has already reached the border, right? Has already reached border, and it's going to start to reflect. But that part of the wavefront has not yet reached the border. It has to travel this further distance before it starts reflecting. Okay, so this particular part of the wavefront at this moment starts to reflect. So you have a reflected beam like that. Reflected beam. We call it R. That guy, on the other hand, takes a little bit longer before it starts to reflect again, because light has to travel first from here to there and then start to reflect, and we call it R prime. Okay. And R prime, R and R prime, as you know, are also parallel to each other. Now, my question is, as the second beam, I prime, just starts to reflect at that moment, what is the wavefront of the reflected beam? Okay, at that moment, the reflection has just started in R prime, right? But it's been going on for a while in R, right? It has already propagated to here. As a matter of fact, you can draw another wavefront. See, this wavefront, okay, this wavefront represents the wavefront of the reflected beam. Okay, at the moment when this beam I prime, the light ray has just started to reflect at the border. All right, now take a look at these two right-angled triangles. There's one and there's two. Okay, they have the same hypotenuse, right? They have the same hypotenuse. And let's take a look at this length from here to there. This length from here to there. How long do you think this length is? Well, it is a time okay, this length going from here to there, we call it time t. Okay, the time it takes to go from here to there, we call it t. So this will be v1 times t. What's v1? v1 is the speed of light in medium 1. This is medium 1, okay? So after a time t, this wavefront has reached there and reflection has started. Meanwhile, what happened to the reflection represented by this light ray at a time t? Remember, at t equal to 0, this reflection has already started, right? And at a time t later, while this guy has traveled to here, that one has traveled to there already, right? So, what is that distance equal to? Well, that is the distance propagated by light in the reflected beam within the same time interval t. So, this distance from here to there is also v1t from here to there. Alright, so now you look at these two right-angled triangles. They share the same hypotenuse, okay? They are both right-angled triangles, and they also have one other side in common, which is both equal to v1t. What can you say about these two right-angled triangles? They must be congruent, right? Which tells us that these two angles, this angle and that angle, must be the same. Okay? These two angles must be the same. And if these two angles must be the same, okay, let's take a closer look at these two angles. This angle is the angle between the incident light ray and the surface, so it's this angle we're talking about. That angle is the angle between the reflected light ray and the same surface, so it's that angle we're talking about. So we have shown that these two angles must be equal to each other. Of course, that means theta 1 must also be equal to theta 1 prime. Okay, so this really is the Snell's law of reflection. We can understand it actually from the point of view of the wave nature of light. So even using the wave nature of light, think of light as a wave, we can still understand Snell's law of reflection. Okay, now the second part of Snell's law is the Snell's law of refraction. Refraction, and that is what happens when light enters the second medium. Okay, upon hitting the surface between the two, the border between the two. Here is the Snell's law of reflection. In this case, the angle of incidence is theta 1. Okay, this is I, right? And this is the transmitted light or refracted light. We call it T for transmitted light, and this angle is theta 2. In general, theta 1 and theta 2 are not equal to each other. Okay, and the Snell's law of refraction tells us the relationship between these two angles, theta 1 and theta 2, and it turns out, yeah, that depends on the ratio of the speeds, v1 and v2. v1 is the speed of light in the first medium, v2 is the speed of light in the second medium. Now we shouldn't be surprised that the speed of light, v1 and v2, enters the discussion, because even in that case, we had a v1 and v1, except these are the same, right? Okay, here we have v1 and v2, so that will lead to the difference in the two angles, theta 1 and theta 2. Let's see how the Snell's law describes refraction. Let's see how we can prove it with our understanding of the wave propagation. The Snell's law of refraction says that sine theta 2 over sine theta 1 equals to v2 over v1. Okay, that is the Snell's law of refraction. And this tells us that if light travels from air to water, okay, then theta will be greater than theta 2, because light travels in air at a speed that's greater than the speed it travels in water. So it's going to get a situation like that. Okay, air to water. If it's from water to air, then this angle will be smaller, that angle will be greater. That is the Snell's law of refraction. How does one prove it? Okay, how does one prove it? Well, again, we are going to consider two incident light rays and two transmitted light rays to see how we can apply the idea of wavefront to understand this law. Okay, let's do that. Again, let's draw a border. And let's draw a normal line. And we're going to draw, again, a set of parallel light rays coming in, incident light rays. Okay, so here is one incident beam, I, and here is a parallel one. Okay, parallel, I prime. I and I prime parallel to each other. And this angle, as you know, is theta 1. Okay, theta 1. At t equal to 0, the first beam has just arrived at the border. The second beam has not yet arrived at the border because the wavefront is like this. Okay, so at t equal to 0, here's the wavefront. The light has only reached this surface. Okay, it's going to take some time for light in this beam to keep on traveling to hit the border. And how long does it take for this light ray to go from here to there? We call it this time t. So this distance would be v1 times t, right? v1 times t. It's understandable. Okay, now this angle, as you know, because this is 90 degrees, this angle is also theta 1. It's also theta 1. Okay, so here you have a right angle triangle with a certain base, and one side is equal to v1 times t. Meanwhile, at t equal to 0, the first beam has already reached the border, so it's going to start to enter the second beam, second medium, and here is what happens when it enters the second medium. Okay, it's going to go this way, and it makes an angle theta 2 with the same normal line. This is theta 2. Meanwhile, the second beam here is going to have to wait for a time t, and then it's also going to enter the second medium. Okay, it's also going to enter the second medium. These two lines are parallel, so we call it t and t prime. Okay, my question is, at a time t later, when t equals 0, we say this beam has arrived, right? At a time t later, what happens to the wavefront? Well, at the time t later, even this beam, I prime, has also reached the border. So the wavefront, as far as this point is concerned, the wavefront is just reached here. Okay. As for the refracted wavefront or transmitted wavefront, this point is right here. Meanwhile, the refraction has already been going on in this beam for a while. All right. So at this moment, the wavefront in the second medium should look like this, 90 degrees. Right? How long does it take to go from here to there? Well, the time it takes to go from here to there is the same time it takes for this beam to travel from here to there. Right? Both time is equal to t. Now, how far did the transmitted wave travel from here to there during the time t? Well, it's the same time t, but the speed is different. The speed is v2, so therefore this distance from here to there is v2t. Okay, v2t. And by the way, what is this angle equal to? This angle is the same as that angle, which is theta 2. Right? Because here is 90 degrees. Okay, so now again we have a pair of right-angled triangles. Here is the first one, and here is the second one. They share the same hypotenuse from here to there, which we call, let's call it L. Okay, from here to there, we call it L. Look at the first right-angled triangle. Sine theta 1 equals to v1t over L. Okay, let's write it down. Sine theta 1 equals v1t divided by L. Right? What about the second, in the second triangle, right-angle triangle? Sine theta 2 equals v2t over the same L. Right? So sine theta 2 equals v2t over the same L. Okay, I can get rid of t and L in one gulp. The way I do that is take this equation divided by the next equation, and what do I get? I get sine theta 1 over sine theta 2. What is that equal to now? v1t over L divided by v2t over L. That is, as you know, v1 over v2. That, of course, is the same as that. Okay, so sine theta 1 over sine theta 2 equals v1 over v2, or sine theta 2 over sine theta 1 is equal to v2 over v1. It is not convenient usually for us to really denote the speed of light v1 and v2 directly. For one thing, they're very, very large numbers. Okay, so what we're going to do is we're going to simply compare the speed of light in different media with the speed of light in vacuum by introducing what's called the index of refraction. Okay, index of refraction. The index of refraction n is a number. N is defined to be the speed of light in vacuum, which is c, divided by the speed of light in a particular medium. Okay? The slower light propagates in that medium, the greater the value of n. And by definition, since wave travels the fastest in vacuum, right? Then in any medium, therefore, by nature, the index of refraction can never be less than 1. Okay, it is equal to 1 in vacuum. In air, the speed of light in air is almost the same as the speed of light in vacuum, but slightly less. Therefore, in air, n is a number that is almost equal to 1, just slightly more, 1.00 something. Okay, and in water, for example, okay, n is about 1.3. That means that the speed of light in water is about 30% slower than the speed of light in vacuum. Okay, so the greater the n value, the slower light propagates in that medium. With that notion, okay, we know that n is inversely proportional to v, right? So therefore, I can write this as n 1 over n2. Right? I can write it like that. So v2 over v1 is the same as n1 over n2. n1 and n2, these are just numbers, which is much easier to deal with than the giant value of the speed of light. So this is the Snell's law of refraction, and we successfully derived it from the notion of light being a wave. Okay, and once we establish the Snell's law of reflection and the Snell's law of refraction, we can pretty much understand how a light ray will behave wherever it goes when it hits the border between two media, what's going to happen, and so on. And with that, in principle, we can make optical instruments because we can predict what's going to happen when you have a certain piece of optical instrument, such as a mirror, such as a lens, such as a spherical reflection surface. We can predict how the light rays are going to be bent or reflected as it gets into a different medium, or as it reflects off of a surface, that sort of thing. So these are the fundamental principles, fundamental laws we use to study geometric optics.